here we go. So since I messed up on the first one, I'm just going to re-explain this slide for anyone who's rewatching for clarification. Well, linear programming, we're talking about optimization. We're talking about maximizing and minimizing functions, finding the biggest that it could be within certain constraints and the smallest it could be. Our solution area is our feasible region. That's a new vocabulary word. Vertices are where the constraints meet. Okay, and those are going to be where our maximums and minimums occur are at the vertices. All right. All right. Let's redo this one that I did wrong. Y'all did it wrong too.
I did mine right. I did mine right.
Come now, guys. All right, so I'm going to give, let's see, I'm going to put the equations up here, or the inequalities up here. These are our constraints, guys. A little bit chit-chatty today in anticipation of the hurricane. And this is our function that we are actually optimizing. This is what we are finding. Notice it's the only one that is not a what? Nope, try again. There you go. It's the only one that is not a linear inequality. It is actually an equation. How do I know the difference? There's an equal sign. What? I think that might hurt your eyes. It is ugly. We'll keep it just because. Whoa now. Hit record, guys. All right. He said go Gamecocks, by the way. He loved the background here. All right, here we go. Here's my axis. I'll put it one more up since it was down too far before. All right, so our lines between 3 and 6, we talked about these are horizontal constraints. Horizontal at 3, horizontal at 6. If you ask questions the first time, ask questions again this time so I have it on the video because that helps everybody. What did y'all say?
Why the lines
Shade in between the lines. You're welcome. Okay.
Only one of them is not an inequality. We said that.
Yes, yes. We said that while we were recording this time, though. It's okay, though. All right, let's graph the second one. Shh, girls. Let's do point at 12. So that's 6, 7, 8, 9, 10, 11, 12. This color scheme is horrendous. 1, 2, 3 over 1. I went 1, 2, 3 over 1 before because it's a little bit easier. It doesn't go off my graph. But whichever, let's connect.
And you can plug in 0 for x. So it would be like y is less than or equal to y.
Correct. There you go.
0.
Good job. So we're going to shade down because that is correct. All right, now we're back to where we left off before. Wait. That's the same one we'd already done before. I was just recapping. It was just that I had counted wrong on the other one.
Did you count wrong on this one?
No, because I counted from the origin here, up 12 from here instead of. I used the wrong origin last time. All right. Third inequality. Why? Because I used this as my origin instead of this. All right, up 6. So this is my y-intercept and down 2 over 1. You starting to see where the feasible region is going to be?
The old triangle. Or the big triangle.
Down or up?
Down.
All right, so nothing new here, right? Everything we have already done. Here comes the new stuff. Actually, still not new quite yet. All right, I'm going to do this in yellow so you can really see it. This is my feasible region, yes? All right, so before I was in the process of giving you steps, and I said your first step was to graph the system of inequalities, right? Your second step is going to be to find the vertices of the feasible region. Come on. I'm going to put FR. If you want to write feasible region in your notes, because you might not remember that FR is feasible region, go right ahead. One of them is easy. They're actually all not going to be bad because we can figure these out algebraically pretty easy without actually solving a system of inequalities. Let me show you what I mean. Oh, I need a black to write over this, don't I? Let's take that ugly orange out. This point's easy, yes? What is that?
0, 6.
0, 6. That's one of my constraints. Not bad, right? Now the other ones that are hard, or they're not hard, they're just a little bit harder. Since they're not, I can't tell exactly by my graph where they're occurring. I can tell where I think they are, but here's what I'm going to do. This line is y equals 6, and this line is what?
3.
That means anywhere on that line, which this point is on, the y is going to be 6, so I don't know the x. And here the y is going to be 3. I don't know the x. Same thing here, right?
Yes.
Thank you. The purple line is y is less than or equal to 3x plus 12. And I don't know what color this is. White is y is less than. And I'm just writing them on here so that you'll see what we're going to do. Now, I've shown you how to do it on your calculator, right? You could put in y equals 6 and y equals negative 2x plus 6 and find the point of intersection on your calculator. This is a pretty easy solve, though, because if I know that y is 6, what line is this one intersecting with? This one, right?
Yeah.
So for this one, if y is 6, how can I find out what x is? Plug it in. And we're not talking about an inequality anymore. We're talking about an equation. So if y is 6, I can solve it, right? Subtract 12 and divide by 3. Does that look about right on my graph? About negative 2, 1, 2. Yeah. You could, but you want to make sure because sometimes it may not be exact. Sometimes it might not be. You can use your calculator to do it too.
And so you're going to use, and see on the homework, I think with this, not exactly this, but I think the last homework we had with this, I got confused because how do you know which function to plug in on? So
you really got to look at which ones are intersecting is what you have to do. So that's why I wrote it on here. If you can tell which ones, like I'm looking at this point and I have to figure out which lines are intersecting.
And you wouldn't use that one because that one on the left has nothing to do with it.
Correct. Now I will use that one when I come down to this point. Okay? And so let's do that together. Now I'm looking at these bottom 2 points. Let's do this one first. Again, y equals 3. You got to look at which lines are intersecting. I've got the line y equals 3, and this line is negative 2x plus 6. So if y is 3, I'm going to have to do a different color. If y is 3, then what is x? And see, maybe you couldn't look and get that just from the graph.
But you're not subtracting
I did. I just didn't show you where I subtracted it. But I subtracted 6 and got negative 3 and then divided by negative 2. Again, on your calculator is fine, This is just, for me, I just assume plug it in if it's something easy like that. And then for the last one, y'all try the last one and see what you get. The x coordinate of this line and this line. Did you get it? What'd you get?
3.
-3?
Yes.
Hold on, sis. Yes,
That one, so follow it up. That one is 3x plus 12. So you see, these are a lot of work, but it's nothing. It's really just built and built and built and built on what we've been doing.
I just think.
No, I'm not done.
Yeah, we.
Right now, we've only done what we already did, right? We found vertices before.
So for word problems, how do you know what you're dealing with? Like where?
I'm going to show you. I'll show you. All right, so then the last and final step is we have to plug each vertex in the function to find the max and min. Well, there's only one function listed there, right?
And that is f(x, y) equals 4x minus.
Correct. So each one of those vertices. So I have -2, 6. I have -3, 3. I have 3/2, 3. And I have 0, 6. For each and every one of those, I am going to plug into, what was my equation?
4x minus 2y.
Thank you. I didn't mean to go up, I meant to go down. So each one. Y'all ready? This is the new part. This is the only new part. 4 times -2 minus 2 times 6. -8 minus 12, which is okay. Go away. Stop. All right, and then -3, 3. So 4 times -3 minus 2 times 3. -12 minus 6 is 18.
Oh.
Uh-oh, it's a fraction. I'm sure y'all are just... 6 minus 6.
How did you get 6?
4 times 3 is 12, and 12 divided by 2 is 6.
Put it into like a decimal. It's like 4 times.
4 times 1.5 is 6. You don't believe me?
That's
Think 4 1.5 times. 4 one time is 4. Half times is 2. 4 plus 2 is 6.
should be 4.5.
And then 0, 6. Let's see. 4 times 0 minus 2 times 6. 0 minus 12, -12. So now my question is, where is the maximum?
0.
This is the... Ooh.
Or you need to get rid of 1.
Max. This is my... I should go, well, let me go a little bit smaller. This is my min.
Cross it out.
No, that's just your maximum occurs at at 3/2, 3, with a value of 0. your minimum occurs, right? Here's your max.
Oh, yeah.
So you have a max of 0. Let me write that for you. Max of 0 at 3 over 2, 3. And you have a minimum of negative 20 at negative 2, 6.
So why are we finding that? And what are we?
We're going to do a problem and application type problem to show you. Which means it's a word problem. We're going to set it all up and then do it. Yay! Recording. This is number 7 from your homework. Transportation. A package delivery service has a truck that can hold 4,200 pounds and has a capacity of 480 cubic feet. Deliveries will only be made if there are at least 10 of each type of package. Okay? So we have 2 package types. We got a little table that's given to us. Package type. They are standard and oversize. Their weights are up to 25 pounds. These are in pounds, I think. Yeah. Up to 25, and this is from over 25. Come on. Up to 50. Anything over that, they ain't shipping. Volume. It's in cubic feet. Standard one is up to 3 cubic feet. And oversize is over 3 up to 5. And then we have the cost. Now, of course, cost is probably what we're going to maximize or minimize, right?
In real life, we could really graph this to figure it out, but it could just be like, whatever the question is, it's going to be what is it, this shit, heavier than this shit.
Well, you might not be maximizing in that particular way. Like if you have a certain number of packages that you need to ship.
This seems like a long way to do something that you figure out somewhere else.
For this one, maybe. But it's a basic example to help you build on a more complicated example. Don't burst my bubble, Marshall. This is
I'm
fun.
just saying that, like, this is unnecessary.
Okay, well then you tell me. You work it your way, okay? And you answer the last question. Determine the number of each type of package needed per truckload to maximize revenue. You said there's an easier. What is the maximum revenue?
I said there theoretically could be an easier solution, not that I know.
Okay,
It's all in the wording.
here we go.
Notice the word.
Part A says, write the constraints for this situation if all the packages are at the maximum weight and volume. Okay, so we're talking at 25, at 50, at 3, and at 5. Okay, so write the constraints. Well, the first thing it tells us is that a package delivered has a truck. It can hold 4,200 pounds. Right? So assuming all the standards are at 25 pounds, 25 times X plus 50 times Y. Do we agree with that? It's 2 different variables. There's an oversized and there's a standard, right? That needs to be less than or equal to what?
4,200.
4,200. All right, the next constraint we deal with is the volume, right? How might I set that up?
X in the middle of the line, B or something.
When it's a graph.
Wait.
3, 3x
Oh, man.
Plus 5y is less than or equal to
480.
maximum volume of 480. That was given in the first part of the problem. Capacity of 480. Now it also says to run the delivery truck, you have to have at least 10 of each type of type. At least 10 of each type of package. How could I say that?
X. Wait, X
Uh-huh.
and Y is greater than equal to
That's
10.
exactly right. X and Y both have to be greater than or equal to 10. Remember, and I can write those as separate inequalities because I'm talking about where they overlap. So both conditions have to be met. You have set it up. You have set up your linear programming problem. I haven't told you what to maximize yet. I haven't told you what to minimize yet. I've just you've set up the system of inequalities. Everybody okay on that? All right, graph them.
Miss Vicky, can you give me an estimate of how much space I'll need for my graph? Because I always like mark how much space.
Well, I'm looking at well, we know we're going to be in the first quadrant, right? Because we're talking about weight. So, what's 4,200 divided by 25?
It's 17.
Is it?
168.
168. So I'd probably go out to about 150 on X and up to maybe 100 on Y. We'll probably go by tens. That'll probably go with me. All right, I'm gonna set mine up while y'all are setting yours up. Yeah, I would just do first quadrant because we're talking about weight and 150. Oh, 15, yeah, because you're going by tens, yeah. All right, so I'll just set up. I don't like that red color. It's not garnet. Yeah. All right, I'm gonna go by tens on my, yeah. I would cover up on this one and find the intercepts. So for the first one, I would do 25x equals 4,200. What did we say that was? 168. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 68. And then I do 50y.
That's 684.
What? Oh, 84. I thought she was 684, and I was like, I think not. All right, 1, 2, 3, 4, 5, 6, 7, 8, about 8.5.
84.
But y'all are just graphing away. I love it. There's no point in really going below the y-axis, the x-axis there because I'm talking real life. Less than's gonna go down. Oh. I'm in this triangle right now. I always color outside. It's okay. Has everybody at least got the first one graphed? Y'all are so busy graphing on your own. Great kids. Sometimes. 3x 480. X is 160. So right here. And then 5y is 480. So y is 96. Is that right?
Yes.
Wait, this one was 8, so that's 96. Ooh, those are awfully close. Again with the down. I think for this one, I'm going to use my calculator. I need to find my feasible region here. Uh-oh. And then my linears are easy. Greater than. And greater than. So if you look, my feasible region, come on. Nope, they're not intersecting there. Yeah, right.
Forward,
Can you put your classroom in the thing that I come from?
All right, this is kind of a crazy feasible region here, right?
So is that a triangle or a quadrilateral?
It's a quadrilateral. Because these two lines are intersecting right here.
And how can you really tell?
And so this one is kind of below that line. So here's what I'm going to do. I'm going to graph each one of these on my calculator. This isn't easy. This is 1, 1, right? That's easy.
What is the maximum thing, you know?
No, we haven't got to it yet. For these three, I'm going to put them on my calculator.
Wait, is that 1, 1 or 10, 10?
10, 10. Thank you. I almost messed up there. All right, so take out your calculator. Now look, this is going to be a little bit harder whenever I graph it. Why? I got to solve it, yep. Right now they're in standard form. I don't graph in standard form, right? No. Listen, I'm with you. I'm right there with you.
I'm ready.
All right. First equation. I'm going to move the 50y and divide everything by 25. I can do that all at one time on my calculator. Okay, if I move the 25x, I've got 50y equals 4,200 minus 25x. And I'm just going to divide everything by 50. I can do this on my calculator just like that. Okay, I'm going to do, open a parenthesis for the numerator because I'm doing some operations in the numerator there. So I'm going to do 4,200 minus 25x, and that entire thing I'm going to divide by 50. That's my first line.
Wow.
Just so that I can determine between the two, if you scroll over, I'm going to change that second one to a little bit heavier weighted line just by hitting enter. I'm not sure how to do that on a Casio.
Oh, shoot, I did it.
Okay, good.
How?
Hit style.
Wait, what if all my lines are straight?
Change one on the pen. And you don't have to do that. That's just something that I like doing. All right. Now for the second equation, I'm going to move the 3x over. So I have 480 minus 3x. Close parentheses. What am I dividing by?
5.
Yes.
So I found the lines, but how do I select the line?
Hit the number that you want.
But it won't let me.
You might have to type. You might have to type the equation first. I think that's the style of your.
Oh.
I don't know. All right, I'm going to zoom 6, and I know that's not going to be enough because that's only going out 10, 10. I'm going to change my window to about what I'm looking at on my graph. We went on X, we went from 0 to what? 170? I'm going to go 180 to make sure. And I'm going to go by tens just like I did on my graph so it looks exactly the same. And then for Y, I'm going from 0 to, we'll go 180 again and go by tens. Window, hit the button that says window. I doubt your calculator's broken. When you hit window, it should look this way. If you want to change it back to, that might be a little thick weighted there.
What was the next res?
10. No. Res?
Hit window again to make a graph.
You hit the rest. Once you do the window. Can you go to extra? Shoot. Correct.
Press graph and graph.
All right. Yep.
You go to your window and I'll see why not need to see?
Has everybody got both lines graphed and you can see that they are intersecting at some point? We have not found that point, but you can see that they are. All right, let's count. Oh,
I found the point.
you found the point.
120.
Yep.
That's what I saw on my graph. That's what I got. Can you go back to your window?
Uh-huh.
Is it math?
I got 120.
Well, I mean, it's
That's exactly right. 120. Second trace is calculate and choose option 5 for intersect.
The first day we had to work on that, it took me like 30 minutes to remember. I hit like all the buttons and try and figure out how to do it.
How many times over is
You press it 2 or 3 times.
All right, for those of you who are still struggling with the intersection, work on that. Those who are done, go ahead and calculate these points. This yellow line
Is the 50.
is the 25x plus 50y. It's going to equal 4,200. And for that one, x is going to be 10. So find the value of y here.
Do I just plug that in
How do
my
we plug in
calculator?
x equals 10 and 2?
Plug not on your calculator. This is the one we do it algebraically. So just put a 10 in for x and solve it for y. And same thing here, but it's the other equation. It's the 3x plus 5y is going to be equal to 480, and you're going to plug in y equals 10 because that's the y equals that it's intersecting. Okay? And find those values because I need 4 vertices and I have 2.
Y equals 79. Yes.
What is it?
79.
79. All right, so I got 1079.
Can we plug that in?
How about this one?
Oh, which one?
Y equals 10 for the other equation.
Yeah. Negative C. Negative 2. Negative 2 divided by 3.
Are you doing this in your head? Why don't you use your calculator?
Answer is negative 0.66.
Negative 2/3.
Yeah, that's it.
I'm sorry, did you ever get a 30?
That cannot be right.
That's me.
I got, but now when I got y equals 709.
Oh, it's 480, not 48.
Oh.
That would be more six.
Oh, this 25 is 25.
What do you get?
You get 143 for X.
That's better.
143.3 would be
143 and a third.
So how did you get 79 to the top one? I got 790.
And you plug
Plug it
in.
10 for both.
It is 790. Right?
That was 79.
How? What?
Oh no, yeah.
250 minus 420 or 450.
What'd you say for this last one for the X?
It's 143 1/3 10.
I stood off.
Hey, yeah,
If you plug 10 in here, you get 250 plus 50y.
Oh, I divided by 5y.
There you go. That's why. It's just a zero off. We did the same thing over here with. Okay, so this has been a lot of work, but this is exactly what we've already done. There's not any new stuff here yet. The new stuff. Well, because last week we found the vertices, right?
now we're
Yeah.
trying to find the maximum.
So now what I want you to do is go back to this original problem. Oh, what a problem, right? Go back to this original problem and write a function that would represent the revenue. In other words, how much money the company makes for shipping X number of standard packages and Y number of oversized packages. How would you figure out? If you shipped a standard package for $12.50 and you shipped an oversized package for $20, how much money would you make?
Well, how much do they cost?
$12.50 and $20.
So that's a shipping fee. How much does it cost?
We're going to assume that's revenue. That's how much they're making off each one. Let's assume they're making that. We're not going to take the other variables into account, which is when it really gets sticky.
What'd you do, 25 times 1250?
Like 312.
Yes.
Oh.
Yes. 1250x plus $20 times y would give you your revenue. Do you agree?
Yes. And so that's
This is your function. At what value would you maximize your revenue? That's the question I want you to answer. At how many standard and oversized packages would you need to ship at the same time to maximize your revenue?
So we use that one.
So you use that formula and you're plugging in the vertices. Okay? So let's do this. This row do... Come on. What? There it goes. All right. This row do the point 1010. This row do the point 1079. This row do the point 12024, and then y'all two rows combined do 143 and a third 10.
How many of 143 and a third? I got
is this
9.
Oh, that's an 8.
143 and a third.
Yes, this last point.
Okay, I didn't even know.
Did it seem like it's less than 8?
We plug 10 in for y, and we solve for x.
Yeah,
So this would be 50. Subtract it and divide it.
I keep doing
It's just because this is so involved and there are so many steps and it is so much. It's tedious, but it's not that it's so hard. It's just tedious. All right, row 1. At 1010, what is our revenue? 325. If you ship 10 standard and 10 oversized, your revenue is $325. Row 2. What happens if you ship 10 and 79?
Yes.
1,705. Is everybody in agreement on your row?
Yes.
All right, so we got 325, we got 1,705. Next row, if you ship 120 standard and 24 oversized, what have you spent?
1,180.
80? And last row. If you ship 143 and a third packages and 10 of the other, what is your revenue? 1,900 what? 25?
143 standard packages and 10 oversold packages. For a grand total of
191 what?
So to maximize here, to maximize your revenue, you would want to do the 143 and a third. No, we can't ship a third of a package. So we're going to go with 143 standard, 10 oversized would give us the most revenue. That makes sense? Takes into account the weight, the volume, the number we can ship, everything. That takes it all into account. How about what's the least you want to do?
the 1010.
The 1010, you only make $325, right?
But how much would it cost for them to ship it? Not how much money that
We didn't take that into account. But we should have, yes. But that would have further complicated
There's
the
a whole
problem.
bunch more stuff you have to take
Yeah,
into account.
yeah. But we're just dabbling in it right now. A true linear programming problem would have a lot more constraints than what this has. All right, yes, no, maybe so?
Maybe so.
Okay.